This is B. Naresh, working as assistant professor in ECE department. And today's topic is common collector configuration with characteristics. So before going to this common collector configuration, we know that the bipolar junction transistor contains three terminals CO, namely that is emitter, base, and collector. So based on this, we define the three types of the configurations. That is one common base configuration, common emitter configuration, and common collector configuration. So in the last sessions, we observed the common base as well as the common emitter configuration with respect to your characteristics here. And in this, we are going to observe what is the common collector configuration and what are the characteristics of bipolar junction transistor under common collector configuration here. So if we are going to construct this common collector configuration, then we need to first identify that the which terminal is acts as a input terminal and which terminal is acts as a output terminal here. So by making this, the collector is a common means that the collector is a common for input side as well as your output side here. And apart from this collector, we have the two terminals, base and emitter. Hence, from these two terminals, the base is connected as the input side and emitter is connected as your output side. Hence, so the base terminal here it is acts as input and the emitter is acts as the output terminal. And input is measured between base and collector. Output is measured between emitter and collector. So from this configuration, we are collecting the output information from the emitter terminal. If we observe the transistor construction, either NPN transistor or a PNP transistor, based on the construction of the transistor, we know that the total emitter current is a summation of base current and your collector current here. In that, so we know that emitter is always emits the charge carriers here. So that is the reason. And from this common collector configuration, again, we are collecting the output from the emitter. Means that how many charge carriers are emitted from the emitter, all those charge carriers are collected at the output side here. So that is the reason. So we can say that this common collector configuration is also called as a emitter follower circuit. So why? Because of that, we are measuring the output across the emitter terminal and where the emitter is acts as the source for an BJT. So hence, how many charge carriers are emitted from the emitter to allow the conduction, and the same amount of the charge carriers are collected by using this output terminal under this common collector configuration here. Hence, from this representation, and by making this a common collector configuration, we need to pass the input between base as well as the collector, and we need to measure the output from the emitter as well as your collector here. So, and coming to this configuration, let us consider, and this is here I consider the transistor type is NPN transistor here. And from this NPN transistor, and this is represented as emitter, and this terminal is represented as the base, and here it is represented as your collector. And based on this NPN transistor, the current flow direction is outside the region, hence the emitter current flows like this direction here and towards base and your collector. And from the flowing of this emitter current towards the base and the collector, here I represented as the direction of the base current as well as your collector current. Now we need to satisfy the definition of the transistor here. We know that the transistor means it transfers a signal from the low resistance input circuit to the high resistance output circuit. Hence, so we need to offer the input side, we need to offer a low resistance And output side, we need to offer a high resistance here. So from this case, a transistor transfer the signal from this low resistance input side circuit to the high resistance output circuit here. To make this a resistance across the input junction as well as the output junction, so we need to recall that the PN diode operation here. If we consider the PN diode and it contains the two types of materials, and those two types of materials are combined, then it forms the PN junction here. So when we apply some external force to and this PN junction, so when the P is connected with the positive pole of the battery with respect to your N-type material here, so hence N is connected to negative pole of the battery. And from this biasing or from this approaching of this energy, here this PN junction is acts as a forward biased diode. Forward biased diode. So when this diode is a forward bias, we know that at the maximum conduction takes place across the PN junction. So whenever it allows the maximum conduction through the PN junction diode, and that particular diode offers the very small forward resistance here. So that is the reason. Under this forward resistance, it offers the diode forward resistance, and that should be very small here. So we know that if the resistance is a very small, hence a maximum conduction takes place across the diode. Similarly, let if the PN diode is biased with a reverse bias, means that when a P-type material is connected to negative pole of the battery and N-type material is connected to positive pole of the battery. So from this approaching of this external force to an PN junction, now we can say that under this biasing, this particular PN junction is acts as a reverse bias diode. So, and we know that when the diode is a reverse bias, it does not allow the flow of conduction here. So that is the reason. Under this condition, the current flowing across this diode is represented as zero, ideally. Hence, it offers very large reverse resistance. So that is the reason. RR is infinite here. So RR is represented as your infinity. From these two principles, we need to satisfy that the input side we need to offer a very small resistance, and output side we need to offer a very large resistance to satisfy the definition of the transistor, or to transfer a signal from low resistance input circuit to the high resistance output circuit. From this, so means input side we need to make that particular PN junction is forward bias, and output side we need to make that particular PN junction is your reverse bias DA. And coming to you, and based on this common collector configuration, and here the collector terminal is common for input side and your output side. And the rest of the two terminals we consider as your one terminal is for input side and one terminal is your output side. And the input is applied between this base terminal and your collector terminal here. And output is applied between emitter and your collector. But if you observe the normal transistor, either NPN or a PNP transistor construction, and this is your emitter, and this is the base and your collector. While forming this transistor construction, it produces the two junctions here. One junction between emitter and the base, another junction is between collector and the base here. So here, and this is input side, emitter base junction, and a collector base junction is your output side. Means we need to satisfy whatever the configuration. Your emitter base junction should be forward biased, and a collector base junction should be your reverse biased here. Either a common base configuration or a common emitter configuration or a common collector configuration. Irrespective of the configuration of a bipolar junction transistor, we should follow that the emitter base junction should be forward bias and the collector base junction should be reverse bias to satisfy the active region active region mode of operation, or to transfer the signal from the low resistance input circuit to the high resistance output circuit. So from this point, now we need to define here. So based on this common collector configuration, we need to show that how this emitter base junction is forward bias and how this collector base junction is here reverse bias. So hence, let us consider, and this is the junction between base and emitter, and this now we are showing that emitter base junction. In this emitter base junction, we considered as the base is the input side, hence, and the type of the transistor. So here I use the NPN transistor here. That is the reason. This is the N-type material. Base is made with the P-type material, and again collector is made with the N-type material. So here the base is made up with a P-type material. Then we are going to show that your this base with respect to your emitter, it should be a forward bias. So that is the reason. This P-type material, and we know that from this analysis, when a P-type material is connected with the positive pole of the battery with respect to your N-type material, we can say that that particular PN diode is acts as your forward bias. So hence, and based on this configuration, the base is utilized as an input terminal, and the base is here is made up with P-type. Why? Because of that here we consider that the type of the transistor is your NPN transistor. Hence, the base is made with this positive pole of the battery with respect to this material. Hence, then this junction, your input junction or emitter base junction, is becomes to your forward bias. Similarly, then output side, we need to show that the collector base junction should be your reverse bias. So that is the reason I taken this as a collector terminal. And now we need to show that the collector base junction should be your reverse bias. And this is made up with a collector. This collector is made up with N-type material. Hence, this collector is connected with the positive pole of the battery. So collector is connected with your positive pole of the battery. Why? Because of the type of the material is for a collector is your N. So hence N is connected to this positive pole of the battery. Then we can say that this is the N-type material. N is connected with the positive of the battery. That particular junction is acts as under reverse bias T. So hence we shown here. So based on this approaching of this VEE with respect to your cathode and the base, so we can say that so in internally the collector base junction becomes your reverse bias here. And with respect to this approaching of the biasing of VBB through this base terminal, we can say that the voltage or the biasing across this emitter and the base junction becomes your forward bias. So hence, and based on the emitter base junction is offers the very small resistance, and the collector base junction offers the very high resistance to satisfy this transistor operation here. So from this representation, now we are going to find out that so what is the current gain of this common collector configuration of bipolar junction transistor. So based on this, and we know that the current gain is represented as your is defined as it is a ratio of output current to the input current. The current gain is defined as it is a ratio of output current to the input current. And in this common collector configuration, and we should represent this common collector is represented as in this current gain is represented as your gamma, or it is also called as DC current gain. Hence, it is also represented as a gamma DC. So gamma DC means a DC current gain under the common collector configuration. So based on the definition of this current gain, we should define that and the ratio of output current to the input current. If you observe this configuration, and from this common collector configuration, output current is acts as your emitted current, and the input current is acts as your base current. So that is the reason. And here we are going to define this current again is represented as, so output current is emitted current, and with respect to your input current is your base current. So hence where IE is represented as emitted current, IB is represented as your base current. From this, I am going to rewrite this mathematical relation. The emitted current is in terms of gain parameter is represented as gamma times of your IB. IE is represented as gamma times of your I. So this is derived from with respect to the definition of the DC current gain. But in general, we know that based on the transistor construction here, and either whatever the transistor, either a NPN transistor or a PNP transistor, and we know that the total emitter current is the summation of base current and your collector current. Means that how many charge carriers are injected from the emitter, and those charge carriers are constituted with the base and your collector. So hence we represented this IE is the summation of base current and your collector current. Now, based on this common collector configuration, we need to redefine the, means we need to define the emitted current is depends upon your applied or input current here. So that is the reason. From this current representation, if you observe this relation, the emitted current is directly proportional to your base current. So hence, we need to rewrite this mathematical relation in terms of your base current. Suppose if you want to write this one, so we need to replay this IC in terms of your base. And we know that again from the transistor construction, IC is represented as alpha times of your IE plus ICBO. So where this ICBO is reverse saturation current, reverse saturation current is absorbed when the collector base junction is your reverse bias. So if the collector base junction is a reverse bias, and we know that, so a particular PN junction is a reverse bias, then it is represented as your open circuit. So that is the reason. When the collector base junction is the open circuited, it allows some current. That current is represented as your reverse saturation current when the collector base junction is your open circuited. Now I am going to substitute this relation, IC relation, in this IB parameter. So hence IE is equal to, this is IB plus IC means, what is IC we defined here? Alpha times of IE plus ICBO. So from this, now I'm going to identify the maximum emitter current in terms of this input current is your base current here. So hence, this is IE. I taken the common terms IE minus of alpha times of I. I taken this is outside here. That becomes IB plus your ICBO. So here, if IE is a common, this is 1 minus alpha, that is equal to your IB plus ICBO. Now this is IE is equal to 1 by 1 minus alpha times of IB plus 1 by 1 minus alpha times of your ICBO. So this is some relation. The emitted current is absorbed in terms of your input current, that is your IB. And we know that from the common emitter analysis here, common emitter configure analysis, we define the beta is alpha by 1 minus alpha. And we know that again 1 by 1 minus alpha, that is equal to your 1 plus beta. Why? Because of that, this is 1 by, so this is 1 by 1 minus alpha is equal to your 1 plus beta, means 1 plus beta means alpha by 1 minus alpha. If you take in this LCM, this is 1 minus alpha plus alpha by 1 minus alpha. This alpha is a get cancel, that is equal to you 1 minus alpha. So hence, from this representation, we know that 1 by 1 minus alpha is represented as 1 plus beta. So hence, I am rewriting this equation in terms of beta. IE is equal to 1 by 1 minus alpha is represented as 1 plus beta times of IB plus 1 by, sorry, this is, so 1 by 1 minus alpha is again 1 plus beta times of ICBOA. And in that, we know that here the ICBO is a reverse saturation current, and that is a very, very small. Hence, if you neglected this reverse saturation current, IE is directly proportional to 1 plus beta times of IB. So this is from the relation. And again, we observe that from the DC current gain definition, we observe that IE is equal to gamma times of your IB. So this is the derived from the DC current gain definition here. And this is the derived from the configuration. IE is represented as 1 plus beta times of IB. If you compare these two terms, if you relate these two terms, and here this 1 plus beta is represented as your gamma. So 1 plus beta we can also write in terms of your gamma. So that is the reason. And this is, we can rewrite this IE is equal to gamma times of your IB. So this amount of the current flows across the emitter in terms of your applied input current, that is your base current here. Same I shown here. Now coming to you. So based on this operation, now here I am going to observe what are the characteristics and how it behaves based on the configuration, means with respect to your common collector configuration. So we are going to observe the characteristics here. So here it contain the two types of the characteristics here. So one is represented as input characteristics, one is output characteristics here. So first we'll see and what are the input characteristics under this common collector configuration. So for this case, if you look at about this a common emitter common collector configuration here. So here I consider this is a transistor, NPN transistor, and this is the biasing here, biasing voltages, what we observed just now. So but here I place some indicating meters to allow the meter to measure the current and your voltage across the input side and your output side. And we know that if you want to plot the input characteristics, so we need to plot the characteristics between input voltage and your input current by making the output voltage is constant. And from this representation, we know that the voltage between the input side, means the input voltage is measured between the two terminals, that is base terminal and your collector terminal. So that is the reason. That voltage here I am representing as your VBC, means the potential difference between base and a collector, that is VBC. Similarly, we are going to observe the current flowing across the base, and that current is represented as your I, means we need to plot the curve under the input side VBC versus IB by making output is a constant. So what is the output here? So means the output voltage is measured between this emitter terminal and this collector terminal. So hence the potential voltage or the potential drop between emitter and a collector is represented as your VEC. So hence here we need to make that VEC is constant. And now we can observe, and this ammeter can be used to observe the output current. That output current is here across the emitter, hence I represented as your emitter. So in this case, if you observe this configuration here, and the VEC means if you observe the normal transistor construction, and this is your N-type material, and I consider the P, NPN transistor here. N, this is P and your N here. And this N side, I consider this is the emitter, and the opposite end is a collector. Middle one is your base. So from this common collector configuration, we are going to maintain or we are going to observe the output voltage is in between emitter and your collector terminal here. So that is the reason we need to observe the voltage between this emitter and a collector, that is represented as your VEC, that is nothing but your a potential difference between emitter and your collector. If you observe this a potential difference between emitter and a collector, that is passing through the two junctions here. So this is one junction, that is represented as emitter and base junction. If you observe this one, that is another junction is collector and your base junction. So hence, if you want to measure this a voltage drop between emitter and a collector, it is passing through the two junctions here. Hence, the one is passing through your emitter and the base junction, one is passing through this collector and your base junction. So hence, before going to observe these characteristics, so here, so how this graph shows like that I'm showing here. Let us take, and if you want to plot the input characteristics, we need to take the input voltage is the VBC versus input current is your IB by making your output voltage is constant, that is the VEC is constant. Let initially suppose if I assume this VEC is 2 volts, I consider that VEC is a 2 volts and I made this VEC is a constant here. Now what happens we'll see here. So from this representation, and this the potential difference between emitter and a collector is a represented as VEC. So or to observe this construction, if you want to measure this VEC, that voltage is the combination of emitter base junction voltage and your collector and base junction voltage means. So that is the reason here I represented this one. So this is the one junction is a form between base and this is the emitter node, and that potential difference between this base and emitter is represented as your VB. Similarly, another junction is a form between this base and this collector, and we need to measure a potential difference between these two terminals in between, that is base and a collector, that is represented as your VBs. So from this here, so from this construction, we know that the VEC is represented as, so we know that the VEC is represented as the combination of emitter base junction voltage, that is represented as VBE, plus another one is collector base junction, that is VBC here. So from that common collector configuration, we derived this one here. VEC is equal to the summation of emitter base junction voltage and collector base junction voltage. But here, to plot this input characteristics under this common collector configuration, so here we need to plot the curve between VBC versus your IB. Hence, from this relation, I'm going to find out this VBC, that is equal to VEC minus your VB, means the potential difference. So here, if you look at this again, this one, so here we need to find out this node voltage from this base to collector node voltage. So means we need to subtract this emitter base junction voltage from the emitter to collector voltage. So the same here I represented here. So VBC is equal to VEC minus VB. And to plot these characteristics, now we need to maintain this VEC is a constant here. So when the VEC is a 2 volts, now what is the output voltage? Means what is the potential between base and the collector. So here I consider this is the 2 volts minus this is the VBE here. Now again, and from the configuration, and here your emitter base junction is your forward biased here. So that is the reason if any PN junction is a forward bias, or when the diode is conducting, it allows the maximum voltage that is equal to your cut-in voltage here. So from that representation, when the diode is a forward bias, the voltage drop across the PN diode is equal to your cut-in voltage. So that is the reason. And from this configuration, this is the one junction voltage, the junction between base and emitter, and this junction is acts as a forward bias junction. So that is the reason. When that particular junction is a forward bias, the voltage drop across that particular junction is equal to your cut-in voltage. Hence, here I represented that one. 2 volts minus the cut-in voltage, here I represented as your V gamma. So from this case, we know that V gamma is either 0.7 volts or your 0.3 volts here. So if it is a silicon material, the current voltage is 0.7. If it is the germanium material, the current voltage is 0. Suppose here I assume that this NPN transistor is made of with a silicon material. Hence, now what happens here? This is 2 volts minus the current voltage for silicon is your 0.7. Hence, the VBC becomes 1.3 volts. So that is the reason. At this 1.3 volts, what happens your input junction is a forward bias, hence it allows the maximum conduction. So let us take this voltage. At this point, the voltage across this VBC is represented as some 1.3 volts here. At this 1.3 voltage, the input voltage, it allows the maximum current. That maximum current I represented this one here. Now we'll see what happens, why this inclined slope will be formed here. So for this case, let us consider if this VBC is increased from so what is the VBC voltage at this point? VEC is the 2 volts, VBC is the 1 volt. So hence it is 1.3 volts to some 1.5 volts. What happens? We need to check. So what is the relation here? This VEC is equal to VBE plus your VBC. Now VEC is a constant, that is a 2 volts. Now VBE, and now what happens? This VBC is changing from 1.3 volts to 1.5 volts. Now, how we are going to make due to this condition? If the VBC is increased from this 1.3 volts to 1.5 volts, how we are going to make this is a constant? That compensation is done through your VBE parameter. How much voltage is increased in this collector and the base junction? That voltage should be compensated through this VBE. So means if you observe this increased parameter 1.3 to 1.5 volts, how much voltage is increases here? 0.2 volts is increases, and that 0.2 volts is compensated through this VB. Hence, VBE is reduced from the cut-in voltage to your some voltage that should be in terms of 0.2 volts. Hence, so previously, what is the current voltage? 0.7 volts. Now we need to compare this 0.2 volts. So hence, VBE is reduced from 0.7 volts to 0.5 volts, and this VBC is increased from 1.3 to 1.5. Hence, this is VEC becomes to your constant. And in that point, so that is the reason I change it. This point is 1.5 volts here. When VBC the change from 1.32 to 1.5, what happens internally? The emitter base junction voltage is reduced to your 0.5 volts. And whenever at the PN junction diode, if the base and emitter voltage is less than of cut-in voltage, so here what happens? This is the cut-in voltage equal to VB is a 0.7 is equal to cut-in voltage. Whenever the junction voltage is less than of cut-in voltage, we know that that diode enters into your non-conducting state. So that is the reason. Due to this dropping of this 0.2 volts in this case, at that particular input side or emitter base junction side, that particular PN junction changes from conducting state to your non-conducting state. So whenever that particular PN junction diode changes from the conducting state to non-conducting state, what happens here? So if it is a non-conducting state means it does not allow the conduction. So that is the reason. Current is reduces to 0. So at this point, when VBC is a change from 1.2 to 1.5 volts, your emitter base junction becomes non-conducting state. Hence, across that emitter base junction, the current is reduces to zero. That is the reason this inclined slope will be observed. So this is happen when VEC is 0, 2 volts here. Similarly, so whenever we consider this VEC is the 4 volts, suppose here when VEC is the 4 volts, so what happens here? This is from this relation, the VBC is means this is 4 and VB is a V gamma. Again, this 4 minus, if it is the silicon type, V gamma is the 0.7, hence this is 3.3 volts. At this 3.3 volts, it allows the maximum conduction. Hence, so let us take this point is this intersecting point here. I represented this 3.3 volts here. Now, we'll see what happens if this VBC is the changes from 3.3 volts to 3.5. So now this is 4 here. This is 4 VEC, and this VBC is the changes from 3.3 to 3.5, and this is 3.5, and this 3.5 we need to compute it. Means again VB is reduces from 0.7 to 0.5, hence it becomes 4. So both are becomes your constant. So at this 3.5 volts, what happens again at the input side or emitter base junction side, the voltage across the emitter base junction becomes less than of your current voltage. Hence, that particular emitter base junction becomes the non-conducting state. So if it is a non-conducting state, again there is no current flowing across that particular diode. Hence, it is reduced to 0 from the maximum current to your minimum current. So this is your input characteristics here. Similarly, if you want to observe the output characteristics here, so means, and from this configuration, if you want to plot the output characteristics, we need to plot the graph between output voltage and output current by making the input current is constant. If you observe this output side, what is the output voltage here? The output voltage is measured between this is emitter terminal and collector terminal. Hence, it is represented as the potential difference between emitter and the collector is VEC. And output current is measured across from the emitter terminal. This is the emitter terminal. Hence, the current is represented as your I. Hence, we need to plot the curve between VEC versus IE by making which input current is a constant. So, input current means your I. So, if you observe this one with respect to this one, here I plot this output characteristics. X-axis is represented as your VEC and a y-axis is represented as your IE by making IB is a constant. So means we are plotting this curve VEC versus IE by making IB is constant. This is for common collector. If you observe the common emitter configuration, we also plotted that VCE versus in output side in the CE configuration. If you consider the output characteristic, we plotted this VCE versus IC by making IB is constant. So based on the construction of the transistor, we know that IC is approximately equal to your I. Why? Because of that, we know this relation IE is equal to the summation of base current and your collector current. And based on the doping levels and based on the widths of the terminals, we know that some 2 to 5% of the charge carriers are only constituted with your base, and the remaining 95 to 98% of the charge carriers are constituted with your collector. So from that representation, the base current is a very small compared with your collector current. Hence, IE is approximately equal to your IC. So hence, this characteristics, if you rewrite this one, VEC versus IE is approximately equal to your IC by making IB is a constant. So if you compare with the common emitter output characteristics, so in the common emitter output characteristics also, we plotted that VCE versus your IC by making the IB. So that is the reason the output characteristics are similar to your common emitter output characteristics here. Or We know that again IE is equal to gamma times of your IB, where gamma is represented as 1 plus beta. So hence, so that slope will means it becomes to your constant of 1 plus beta times of your given base current here. And from this region, and this is the left side portion, so when VCEC is less than 0, then it becomes a forward bias, hence, and already implemented in the forward bias, and this region here, it is represented as your saturation. And from this point here to this point, what happens here? Emitted basing is a forward bias and the collector basing is the reverse bias. Hence, this region here it is called as active region. Whenever this IB current is a less than 0, means there is no flow of charge across the base terminal or input side junction here. So what happens here means that the junction is behaves like your reverse bias junction. So that is the reason. If the emitter base junction is the reverse bias under when IB is a less than 0 and already collector base junction is the reverse bias, hence this region is called as your the cutoff region. So these are the some output characteristics of common collector configuration. So up to this point, so we observed that what is a common collector configuration and what are the characteristics of common collector configuration here, input characteristics and your output characteristics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.